Okay. Okay. Now that we've described minimally changing memory chips, let's talk about 3D stacked memory. I believe this minimally changing memory chips is applicable to many different memory chips also. So people have actually been looking at SRAM, doing similar types of computation inside the SRAM circuitry. There are several papers related to that now. And as I said, phase change memory. I think there's going to be more and more of this. And the design of the memory chips to do computation, maybe not as minimally changing, but a little bit more changing the memory chips is going to be more interesting going into the future. But let's talk about this other thing over here, exploiting 3D stacked memory, because this is something that's already happening. And we basically have 3D stacked memory plus logic today. And this is one example, Hybrid Memory Cube Consortium. You have a logic layer underneath DRAM layers that are connected with each other through silicon vias, high bandwidth connections. And there are many of them, which means that you can do processing inside the logic layer that could be manufactured in a different way than the memory layers. That remains to be seen. And there are other 3D technologies that are under development with better connections between the memory and logic. In fact, you could fabricate logic memory, logic memory, logic memory. And there's some work at Stanford, for example, in the next project by Subhasish Mitra and Philip Wong. They're looking into these things that are really, really interesting, in my opinion. They're more true 3D, but they're a little bit more out there.
They're monolithic.
Yeah, they're monolithic, actually. Yes, that's right. It's better integration technology. So
Very nice.
if that succeeds, then you're basically doing processing very close inside the memory structures, almost, right? But this is something that already exists. Can we enable it to do processing? That's very powerful. And this was what I showed you yesterday, the Ramlater paper. At the time it was written, there were a lot of 3D stacked memory technologies, as you can see over here. And this is going to increase, in my opinion. And if this true 3D stacking, monolithic integration happens, I think there's a lot more opportunity for it. So we had two key questions in 3D stack processing in memory when we first started this. And I'm going to start with the first one. How can we accelerate important applications if we use 3D stacked memory as a coarse-grained accelerator? Basically, we have all the freedom we want. We can change the architecture and the programming model. And we can add mechanisms for acceleration. And what are those things? And we're going to also go back to the minimal approach. It's good to examine maximal and minimal whenever there's a new technology. What is the minimal processing and memory support we can provide without changing pretty much anything in the system as much as possible? No changes to the coherence, no changes to the virtual memory, no changes to the sequential programming model, while hopefully achieving significant benefits. So we're going to talk about both. But the first one is going to be a lot more disruptive to the system. We're going to do away with coherence, for example, in this one. So let's start with that. And when we first started looking into this around 2013 or so, our target was graph processing. Because graph processing is very fundamental, I think. It's been used in many of these social media and Wikipedia, whatever you have. It's been used in bioinformatics increasingly. People want to represent things as graphs because they can more easily manipulate new data inside the representation of the genome, for example. It's been used in many, many things. Machine learning, for example, relies on many graph processing frameworks. And last time I gave this talk at Facebook, they were quick enough to correct me, saying that it's not 1.4, it's 2.2 billion now. I don't know if it's going down after the recent stuff, but we'll see. And that's why when I added circa 2015 over here. I don't want to update any of these numbers. They can remain the same for me.
Well, maybe if you wait a few years.
Yeah, maybe, yeah, I see. I see, yeah, but I don't want to count on that. Okay, so scalable graph processing is actually challenging. This is some result in the paper, basically. We've shown that with PageRank-like graph computation, you can throw cores at the problem. You can quadruple the number of cores, and the benefit you get is very little, about 40% performance improvement. And this has been shown many times. It's very much memory bound. And this is one example. This is a PageRank-like computation. Of course, this is very simplified, as you can see. I'm not going to go through the details, but what you have over here is you have frequent random memory accesses because you have these neighboring nodes that are far away from each other. They may be completely random. And very little amount of computation. As you can see, the computation is very little. It's a multiplication and addition over here, right? So this is really exercising that energy bottleneck that we showed, right? the computation is very cheap in terms of energy. Memory access is very expensive. You're always doing memory access, bringing data into the caches. You're never reusing it. Well, almost never reusing it. As a result, you're paying all of this energy penalty without getting any benefit from bringing the data into the processor. I'm not suggesting all graph processing has only random memory access. There's actually some part that has very good locality. There are some parts inside the graph processing system. But not everything is completely random, basically. Yeah. It's dominated by random memory access, no question about that. But there are some local data structures that you manipulate. Yeah. Exactly, yeah. Exactly. The data structure representation helps, but of course, as you scale your data to be very large, I don't know how those things really work.
I don't think there are clever people like that. Just too clever.
Okay, maybe you guys can discuss this offline. But yes, certainly, actually, a lot of the graph processing implementations that we have are based on adjacency lists over here that still have a lot of random memory accesses. Okay, so basically, this is the system that we built from the ground up. This is one slide summary of the entire system. I'm going to go through this. There's a lot in this paper. Actually, this is a paper that we assigned for review. And I don't know if you go on to talk about the review papers sometime, Roman. Not right now, but we can do it at the beginning of the next session, perhaps. But this is one of the papers that I assigned as review. This covers a lot of architecture and system and programming level issues. So this is, in a nutshell, the system. Basically, we start with these memory plus logic chips. And if you look inside the logic layer, you have these vaults. Each vault has a controller that controls a stack on top of it. Let's say 8 memory stacks, but you could also increase it. And these vaults are connected to each other via some network, so they can communicate quickly with each other because this is on chip. And each vault has a DRAM controller, and we add a very simple in-order core to it. And we add some messaging mechanisms such that we could program this with message passing, as you can see. And we add some prefetching mechanisms that I'm going to very briefly touch upon. So the basic idea is these vaults are processors, and they communicate with each other. And if you want to operate on a graph node that is housed in some other vault, you send a message to that node saying, node, please perform this function on that data that you house. That's the idea. Basically, you program this using message passing. Whenever you need some data from some other vault, you send a message to the core that houses that data saying, perform this function. It's basically remote procedure call-based programming. And if you actually want to scale up the system, which you really want to with large graphs, what you need to do is basically you interconnect these hybrid memory cube or high bandwidth memory. In this case, we assumed hybrid memory cube parameters. But these 3D stacked logic and memory chips like this through some sort of interconnect, as you can see. I think we use Dragonfly in this case. But interconnects are, of course, important over here. Interconnects is very important inside as well. But here, you actually don't want to go off-chip because you're subject to off-chip bandwidths over here. As much as possible, you want to remain within a single chip over here. So you're really limited by how much memory you have within the single chip. Let me finish this, and then I'll take the question. Basically, if you have a graph, you partition your graph on top of these, which is a hard problem. Ideally, you would like to partition it such that you operate on the local parts as much as possible without communicating across the chips. That's not easy. But in the paper, we analyze, actually, if you do better graph partitioning, you're getting better performance. But you can always do better graph partitioning, especially as your graph size grows. And then the communication is very similar across the nodes over here as we do within the nodes. So in the end, you're really limited by how well you've partitioned your graph over here. There's no question about that, and that's not an easy problem. And we map this to a host processor. It's like you can think of it as a GPU, basically offload and the entire graph processing over here, and it keeps executing. Yes?
Suppose someone took a 1980-something paper on parallel computing with a torus or something like that,
Mm-hmm.
with each node having its own memory.
Yeah.
And said to you, look, we're actually doing the same thing, except technology is advanced,
Yeah.
so people know how to put all this
Mm-hmm.
on a single chip.
Yeah. So it's not a single chip, but I agree with your point. So this is actually very similar to the 1980s message passing based models, except the difference is you're doing processing inside the memory. So all of the other things that I mentioned are actually a lot of parallel processing concepts, no question about that.
You're not doing inside the memory, you're doing inside the memory chip.
Yes, that's right, the logic layer, yes.
The logic is there, so in fact, since the 80s, they learned how to shrink it and put it together.
Yeah, I think technology has enabled something like that.
Yeah, so
Conceptually, I agree with you. Yeah, I agree with you. Like,
unlike the previous thing, which was really in memory, you were doing things differently.
yeah, exactly. So I think if you look at, for example, Bill Daly's M machine, it has a very similar structure actually, and I've had discussions with him related to this. The main thing is the technology is different, so that you can actually enable things like that. So I think that's a very fair comment. And basically, we customize things for graph processing a little bit. That's the other thing. So we have these graph processing specific prefetching mechanisms over here, which I'm not going to go into. So basically, you program this with communications via remote function calls. You have this message queue inside the logic layer such that you can communicate. And basically, you convert your program such that you could use puts and gets. Again, I'm not going to go through this in detail, but you can put a function, and basically you can send it to some other vault that houses the data. And we have blocking and non-blocking remote function calls. You can read the paper for details. And you have barriers so that you ensure that you're done with all of the function calls until, so that you can proceed beyond the barrier. And you can delay it until the nearest barrier also. Okay, hopefully that's, I mean, these are not necessarily new parts, but some of the old technologies can be enabled in memory with this. Okay, I'm going to skip this one. You can read it in detail. Basically, it's a remote procedure call-based programming, remote function calls. If you've done distributed systems-based programming, it's not that different, really. How many people have done distributed systems programming here? Remote function calls, RPCs, okay? Not many. How many people know what an RPC is, remote procedure call? Okay. Okay, I mean, there's nothing really special about it. You basically send the function to be executed somewhere else. Some other server is executing the function for you, and the client is sending that function. You send the function, you send the arguments to the function. In this case, you send the function pointer. And this remote core is basically executing that function for you with the arguments that you provide. And if you want, it's returning the result. That's the idea. It's very simple. It's employed in distributed systems programming because you have a client-server programming model, and the client can ship functions to the server executes them, returns the result back. Right? And it's very similar here. You can think of each of these cores as clients and the servers are the ones that are housing the data that you want to operate on. And whenever a client needs that data, it sends a function to be operated on that data. That's the idea. Okay, and we actually have some prefetching mechanisms that take advantage of the message passing model, as well as some locality in the graph processing, so that you can do linear prefetching over here. But I'm not going to go into that in detail. Although I'll say that this is very important, as you will see in the results, because these simple in-order cores, there's an in-order core underneath here. We have to put very simple cores inside this logic layer, inside the vault, because in the end, this structure is thermally limited. What happens is you have this logic layer. On top of that, you put the DRAM layers. Now, heat has nowhere to escape, meaning that you generate a lot of heat because of the computation here. So if you have a lot of computation here, you have a power and thermal problem in the end. You can try to cool it, but then there's no place to escape over here. As a result, these in-order cores really need to be simple. Now, if they're simple, they're not really utilizing the memory bandwidth that is really available to them. As a result, you have a lot of slack in the memory bandwidth that you can exploit with prefetching if you can take advantage of the prefetchability of the workload. Okay. There's a lot more detail in the paper, and you can take a look at it. And actually, you should review it if you're taking the course. But we've compared this system, which is going to appear here later on, to a bunch of systems. This is the DDR3-based system. As you can see, it has 32 out-of-order cores. That's our comparison baseline. This is the hybrid memory cube-based system. You get higher memory bandwidth available to the cores, 32 out-of-order cores. This is a system for comparison purposes. This has 512 simple in-order cores like the ones we employ. And it has the same memory bandwidth. It's called hybrid memory cube many-core in-order cores. And this is the Tesseract system. It doesn't look like any of these systems because it combines processing and memory together. There's no dichotomy between memory and processor, as you can see over here. They're just together. And in this case, we have 512 Tesseract cores. And as you can see, this is the bandwidth available to all 512 of the cores. It's 8 terabytes per second, which is much higher than any of the systems over here today. Because you don't need to go through these very frequency-limited interconnects and bandwidth-limited interconnects. OK, so this is the results in a nutshell. Compared to the DDR3-based system, normalized on 5 graph processing algorithms that are detailed in the paper, Tesseract without prefetching buys you about 9x performance improvement. And if you add prefetching on top of that, it's about 13 to 14x, which is not bad, I think, although we've changed everything in the system, as you can see. Although you may argue that this is the same as some of the 1980s systems. So if you start with that baseline, maybe it's not a huge change. But if you start with this baseline over here, it's a huge change, actually. Is it worth it? I don't know. 14x is not a bad number, I think. And maybe we've not really optimized a lot out of the system. Maybe you can actually push it to, I don't know, 25, 30x. I don't know. We'll see. OK, so where are the benefits coming from? Partly because we're exploiting memory bandwidth quite well. So these are the other systems over here. They can exploit memory bandwidth. They don't have a lot of memory bandwidth to exploit, and they're exploiting as much as possible. In this case, we have 8 terabytes per second, and we're exploiting about 2.9 terabytes per second. It's not the entire thing, but it's not that bad also. So, and we've also done some other studies to look at, because we're changing the bandwidth, we're changing the programming model. You can say, oh, maybe in the existing system, you magically have this bandwidth. You'll gain all of the performance. You don't need to change the programming model. It turns out that's not true. This is the hybrid memory cube with many core. And if you magically give it 8 terabytes per second, you get about 2.3x. And if you actually have Tesseract change the programming model on top of that, you get about 6.5x compared to the baseline over here. So some of the benefit is definitely coming from the additional bandwidth that's enabled, but a lot of the benefit is coming from the other changes, which are bundled as the programming model over here, message passing, and this doesn't even have prefetching, as you can see over here. And you can do this study in a different way. This is hybrid memory cube with many core, with conventional bandwidth, and this is Tesseract with conventional bandwidth. You don't have 8 terabytes per second. Both of these have 640 megabytes per second. As you can see, we still gain about 3x in this case, because you can exploit, you're closer to memory, and also the programming model is different. So the benefits are not just coming from bandwidth, not just coming from programming model. It's really a combination of both. OK, what about energy? There's some energy analysis in the paper. This is just one example result. As you can see, the energy savings is also significant compared to the out-of-order baseline, where we don't even look at the out-of-order cores power consumption over here. So if you add the out-of-order cores, this is going to be too much. But you get at least 8x energy reduction on average across the 5 graph processing workloads. Why? Because you're not moving data as much. OK, so let's talk about the advantages and disadvantages. I think I'll use this in some of the works over here. So this is a specialized graph processing accelerator using PIM, processing in memory. It gets large system performance and energy benefits, and it takes advantage of 3D stacking for an important workload. But if you think about it, this is more general, right? There is very little specialized for graph processing here, aside from the prefetching mechanisms. You could use this for other workloads also, in my opinion, like machine learning and whatever is limiting you. Of course, there are disadvantages. Basically, we change a lot in the system. New programming model, new. Specialized Tesseract cores for graph processing. And the cost may be high. And I think the biggest issue, I think this is true for all parallel systems that I know of, is scalability is always limited by your off-chip links or how well you partition your program on top of the distributed system that you have. I'm not sure if you can solve this problem, that's great. But I think this is where the monolithic integration technologies can help a lot, because if their scalability is much higher than what we have in these 3D stack chips, those could actually provide a lot more performance. But that remains to be seen.
But what is your object function with the partition? What you need to minimize in the partition of the graph? You have a big graph, and you have a partition.
Yeah.
What do you define the object function?
Basically, you would like to maximize the bandwidth, right? The usage. Basically, you would like to minimize the communication across these off-chip links.
Across the partition, this is what you define, or
You would like to minimize the communication that goes across the off-chip links. You have some size.
but how it's translated in terms
Yeah.
of graph.
Yeah, I think there needs to be a mapping that needs to be done. And we didn't explore this a lot, but you can read the paper for some. I think there's more research to be done in this area for sure, but it's not easy. Okay, any questions? Yes. I did mention the automata processor. I didn't. Well, I did actually have a picture of it. This is Micron's automata processor, right? Mm-hmm. Yeah. Oh, I would say it's a very different approach because automata processor does the processing inside the row buffer, as far as I understand, and it uses the deterministic finite automaton. So it's very limited. Whereas here we're putting a full general purpose core. It's a very simple core, but it's fully general purpose. So you can do anything in this core. Yeah. I think that model is very interesting, but in my opinion, it's very limited. Yeah. So I think in the automata processor, there's no logic layer. I don't think the automata, is that true?
There is very little.
Very little, but yeah, it's not used for, basically you cannot do much with it.
Oh no, the logic there is to...
Huh? Okay, I see.
The logic there is just to prevent the explosion of states in state machines.
I see. Yeah, basically
counters,
that's... Mm-hmm.
basically just counters.
Yeah. It's not very flexible.
No, just
okay.
counters.
Yeah.
But this is... It's a state machine.
Okay, yeah. Yeah. But this is very flexible. I think that would be the major difference. Here we can do anything. It's really a fully, yeah, whatever, you can do anything very flexibly. Say it again?
Completely different approaches.
Yeah, okay.
There's no connection there.
Okay, another question?
Yeah, I have a question, maybe totally out of place in this case.
Sure, I'll defer it.
There's growing talk about memory disaggregation, data centers.
Uh-huh.
Put all the memory together somewhere,
Mm-hmm.
not at the nodes.
Uh-huh.
Now, on one hand, it contradicts all the issues of communication, etc.
Yeah, yeah.
On the other hand, if you do in-memory processing, then it's less critical to put all the memory together.
I agree, yeah.
What's your take on that?
Yeah, I think I agree with you. Basically, if you disaggregate without doing in-memory processing, my feeling is not a good idea because you're exacerbating all the latency issues that we have in the system. And we're going to talk about latency, and I think we should be reducing latencies. That's good for everything. But if you actually do in-memory computation, then it may actually make sense to disaggregate memory somewhere else, and then if you do a lot of processing over there. Maybe these are called in-memory compute nodes, and the other nodes are really full-blown processing nodes. Okay. Okay, so this is the paper that is assigned. Hopefully you'll enjoy reading it. It covers a large design space. And we're going to talk about more. So this is one thing that we studied in 3D stacked memory. So somebody asked about the workloads earlier. What are the other workloads that may be interesting? And then we more recently looked at these devices, basically. I think these devices are actually very interesting because they're very energy constrained. And we wanted to understand what could be done for data movement in these devices. And I'm going to talk about this work that was very recently published in S+. I'm going to use some of Amirali's slides. So basically, consumer devices are everywhere, and energy consumption is a first-class concern, clearly. And we wanted to examine some workloads. We did this in collaboration with Google. We spent some time at Google to understand these workloads. I'm not going to cover all of these. These are very interesting workloads also. They're employed in many things that are used in our lives. I'm going to cover a couple of these, not in a lot of detail, and the paper has a lot more detail, of course. So first thing we wanted to understand was, what is the energy cost of data movement? So there's data movement everywhere in a mobile system. And we did some analysis, and the paper details this. More than 60% of the total system energy is spent on data movement in these workloads. And we wanted to examine the potential solution of moving computation close to the data. In this case, we didn't want to change the entire system. Basically, what we're going to do is function offloading. If we get to a nice function that we think is good for offloading to processing in memory, we're going to offload that over there. So it's a much more practical change compared to Tesseract that we just discussed. But the challenge here is you have limited area and energy budget inside the logic layer. So we're going to assume 3D stacked logic and memory. So how do we do that? Basically, the second key observation, among the workloads that we examined, a significant fraction of the data moment often comes from simple functions. And the paper details some of these functions. Copy and initialization is some of them. Compression, decompression is another example. And we can actually design lightweight logic to implement these simple functions in memory. And when I say in memory, it's in the logic layer. And we looked at two approaches. One is having a small embedded low-power core, similar to Tesseract, but even more stringent, with some SIMD acceleration. That's usually very helpful. And small customized fixed function accelerators. And I think this is actually really important. If you have a logic layer, it's good for that logic layer to be configurable such that you can offload specialized computation on top of it. I think that's a very good way of designing it. In this case, we assumed that you had specialized accelerators based on the workloads that we examined. And these are the results. Basically, you can improve performance, reduce execution time by about 54%, and reduce energy by about 55%. Basically, improve both energy and performance by about 2x. It's not the 13x, but it's not that bad also. So let's look at some of these things very quickly to understand what might be offloaded. There's a lot more detail in the paper. I'll start with the Chrome web browser. I'm not going to cover a lot of things, but this is how Chrome renders a web page. The paper has a lot more detail. Oh, OK. Basically, you need to do loading and parsing of the web page first, and then you need to do the layouting. So you calculate the visual elements and position of each object. And then you need to do rasterization, painting, paint the objects and generate the bitmaps. And you need to composite them, assemble them into a final screen image. So it's a long pipeline. And we've analyzed a lot of it. And browser must provide fast loading, smooth scrolling, and quick switching. I'll leave you to read these from the paper, but I'm going to look at the switching between the tabs, because that leads to some compression and decompression, which is actually more general than just browsing. So page scrolling you can read in the paper, which is really interesting. But tab switching, we can take a look at that. OK, so what is tab switching? What happens during tab switching? Chrome, in this case, employs a multi-process architecture. Each tab is a separate process. And you basically do context switching, and you do the loading of the new page. And it turns out this is a memory-consuming operation. How fast a new tab loads and becomes interactive is important, and memory consumption is important. And Chrome, at least, uses compression to reduce each tab's memory footprint. So you basically, if a tab is inactive, you compress it and put in DRAM, and this is called ZRAM. It's compressed RAM. And then you need to, if you want to go to switch to another tab, if you have a lot of tabs, for example, which I have in my machine. I sometimes have hundreds of tabs, which is not good. But yeah, you need to decompress the tab and use it. Yeah. And you run out of memory. So we did the study. During tab switching, we emulated the user switching through 50 tabs. And we basically looked at the energy consumption. It turns out compression and decompression themselves contribute to about 18% of the total system energy. There are other stuff that's analyzed in the paper. And a lot of data moves between CPU and this compressed part of the main memory. So we wanted to answer this question. Can we use PIM to mitigate this cost? So this is the CPU-only timeline of execution. So you swap out N pages to memory, and you have some uncompressed pages, and you compress them and put them back in ZRAM. So CPU is basically on the critical path. It turns out people can use actually compression accelerators, but it doesn't reduce the data moment. It accelerates the compression itself, but it doesn't reduce the data moment. So we wanted to reduce the data moment. So if you have processing in memory capability in the processing, in the memory, you swap out N pages, and uncompressed pages remain in the PIM engine, and the PIM engine compresses them and writes them back inside memory. So there's no off-chip data movement, and now the CPU can be free. It can do other tasks. So you save both energy, data movement, and you save also CPU capability. And the paper actually has detail in terms of how you do the compression and decompression. Yes?
So if you move the data uncompressed, aren't you using more bandwidth because of that?
So basically, yes, you're using a lot of bandwidth over here. But we're not using that bandwidth over here. So basically, if you want to swap out N pages, what Chrome does is basically it brings in some uncompressed pages, compresses them in the CPU, and puts them back in memory. Basically, we want that process to happen only in memory.
But if you're, let's say, if you're decompressing
Yeah, that's right. So this is the compression part there. The compression part is on the other way, yeah. Yeah. Okay, so.
But this is made that we're acceleration, the compression function.
Yes, exactly. Exactly. You can think of this as a compression accelerator, yes.
Compression accelerator.
Yeah. And it's more general. That's why I wanted to discuss this, because it's more general. If you want to do compression for whatever reason, you could do it in memory this way, as opposed to bringing everything into the CPU.
And also maybe you can, economize bandwidth because you can compress in memory and pass the compressed data to the CPU, and then the CPU can uncompress. No? You can compress your data in memory.
Yeah, exactly. You can do the decompression in the CPU, yes. Okay. Yeah. So both functions actually benefit. I'll leave that to you to read the details in the paper. But let's take a look at another workload. Okay, I don't know why this is doing this. We've also examined the TensorFlow Mobile. This is basically the inference engine that executes in Android phones. And it's basically a neural network. You want to do inference, and that gives you a prediction. And it turns out the 57% of the inference energy in the neural networks that we examined, and we used a bunch of neural networks to examine this, is spent on data moment. And actually 54% of the data moment comes from not really doing this function, but really managing the data reorganization. Again, this is very fundamental. You pack and unpack data such that it can be processed by a layer, and you also quantize data for whatever purpose so that you can actually process it in the way you want it. And these actually are the biggest energy consuming parts, or data moment parts in TensorFlow Mobile. So what is packing? Basically, packing essentially reorders the elements of the matrices to minimize cache misses during matrix multiplication. And these are some results from the paper. Up to 40% of the inference energy and 31% of the inference execution time happens because of packing. And data moment accounts for about 35% of the inference energy. So it's essentially a data reorganization routine. It requires very simple arithmetic. So it's a very good fit for doing inside memory. And this is just one example, right? You don't need to be doing inference or any machine learning to require data reorganization. If you're doing a lot of matrix operations, you may also need data reorganization, right? Quantization, this is basically you take a floating point value and you quantize into an integer, for example. And that's what's used in TensorFlow Mobile. You take a 32-bit floating point value and quantize it to 8-bit integers to improve execution time and reduce energy consumption. And this comes at a cost of energy and execution time, and majority of the quantization energy actually comes from the data movement. And basically, this is also a simple operation. It's a data conversion operation. You have shifts, addition, and multiplication operations. So these are actually very good fits for putting into processing in memory. And I don't have the graph over here, but the paper has the graph which shows you move these functions into the memory so that you minimize the data moment. So we evaluate these with simulation. I'll give you some basic results. These are the system configuration. You can take a look at it in more detail. And these are the results. I didn't cover all of this, but this is the compression and decompression in the Chrome browser. And this is the normalized energy. And this is CPU only. And this is what happens if you use PIM core. So you get significant benefits if you offload these functions to the PIM core. And if you actually have an accelerator that's specialized for that function inside the logic layer, you get even more benefit. And this is the packing and quantization. Compression and decompression actually benefits a lot more from the accelerator, whereas packing and quantization, they're even more bound by the data moment. So they don't benefit a lot from the accelerator, as you can see over here. But they both benefit from the data moment reduction that comes from processing in memory. And I didn't talk about video playback and capture, but that's also benefiting a lot from the data moment reduction. Okay.
Is it also faster?
So this is energy, sorry. Yes, it's also faster. This is the energy graph over here, and this is the, okay, I'm going to skip some of these. You can take a look at it in the paper. And this is the runtime. Yeah. So energy reduces, but runtime also reduces significantly. So clearly some functions benefit from the accelerator more, right? The compression and decompression. Accelerators help, data moment helps, and accelerator on top of that helps even more.
But how did you come to this realization? What do you assume about the frequency of the logic you have on your memory?
Yeah, those are all in the paper, basically. Yeah. I mean, it's a huge design space, of course. First of all, how do you? It's a full workload study. So how do you decide what to offload? That's what we wanted to look at. And what are the parameters of your memory side? Sure. I don't remember it off the top of my head, but it's in the paper. But it's not as fast as your processor because we're really limited by one thing that we were really conscious about was the area as well as the thermal budgets that you have in the logic layer.
Oh, and that's CPU only, so you didn't even compare it to GPU, right?
Yeah, we don't have GPU here. That's right. There is no GPU over here. This is all CPU only. Yeah. Yes?
What about the entropic coding part of the compression and decompression? The treating the tree of the coding and the coding, is it convenient inside the memory?
Yeah, I mean, that's why you don't gain a lot of speed up unless you come up with a specialized accelerator. So as you can see, the specialized accelerator buys you a lot in terms of speed up. So you need to specialize the logic. If you don't specialize it, then you don't gain a lot of speed up. You gain some, as you can see, but not a lot. So the compression and decompression are not easy. I agree with you. But some other things are much more easy. Sorry, TensorFlow over here, for example. This is the entire TensorFlow. Yes?
What's the packaging assumption on the baseline for comparison? For example, can I put it as the memory and the processor as a multi-chip module?
Mm-hmm.
Does that change the difference? Because some of the benefits is architecture, some is the packaging, that you're inside the memory chip.
That's right, yes.
Whereas if it's just separate chips on a PCB, then one could do better by simply bringing the dies closer together on an MCM. The question is how much that becomes.
Yeah, I mean, we were looking at things like this. So we're very constrained. We don't really change the packaging as much.
Yeah, the question is what they're doing, whether they bother to do a multi-chip module
Mm-hmm.
with the memory on the same module,
Yeah.
which could have bought them, if they hadn't done it already, may buy them some of this benefit. Just
Yeah, maybe. Yeah.
reducing energy and cost.
Yeah, I mean, we didn't really explore all of those packaging directions. No, that's true. We assume basically you have 3D stacking.
For you.
For us, yes.
Yeah, question for them. For you, I understand.
Yeah. Yeah, we can take it offline, I think. We can discuss a little bit more on this one. Okay, any other questions?
Do you have analysis for the training part also, not for the inference?
No, I mean, yeah, I think that's very interesting, but
And also, a lot of tensor or this machine learning are they are computer intensive benchmarks because you are doing their matrix multiplication.
mhm,
Because
yeah.
you are doing n cubic operation and bring n quadratic operation from the model, n quadratic data from the
Yeah.
Not really, because you multiply in vector matrix, not matrix matrix.
yeah, no, matrix matrix, not vector matrix.
Only if you're batching.
No,
Only if you're batching.
usually you batch when you have you have some.
So,
Usually you do matrix
so
by matrix.
yeah, so I think in the end it depends, but we're not offloading the entire inference. We're offloading really these data reorganization and data packing, data conversion operations.
The data organization.
Exactly. So the rest is done in the CPU, basically. Yeah. Okay. Okay, let me. Okay, there's more in this paper. You can take a look at it. Okay, so what else? I think we have we'll have some more time, but I'll get to a natural ending point before we take another break. So there's a lot more to do in this area. We've been looking at GPU processing. Certainly, you can do this in GPUs. This is one example. You may have a main, very powerful GPU, and that may be aided by a bunch of GPUs that are underneath memory stacks. Of course, these GPUs may not be as powerful as the main GPU, right? And we've been looking at systems like this. How do you do the offloading over here? What kind of performance gains do you get? I think these are really interesting, but I'm not going to cover them. And there are certainly scheduling issues related to this. I'll talk about pointer chasing a little bit because this is exploiting the latency benefits of pointer chasing. I'm not going to cover, maybe I'll cover it very quickly. This is something that we looked at. We wanted to accelerate pointer chasing inside the main memory, essentially. And there are a bunch of challenges. And one of the challenges is address translation, actually, which is still an unsolved problem, in my opinion. And our solution was actually a specialized accelerator inside the main memory. And there are two ideas. We actually had a decoupled access execute engine, address access decoupling, enabling parallelism inside the accelerator with low cost, and a page table structure inside the main memory. It's low cost. But again, I think this is an open problem, but I just want to describe this to give an idea of this open problem. So these are the results that we achieved. Basically, we got about 20% to 90% speed up for pointer chasing operations, and if you actually port a database on top of it, you get about 16% throughput. Maybe not that high. And some reduction in energy consumption. So let's go through this a little bit, because I think this is an important thing, and it's not easy to accelerate these applications, linked data structures. They're used in many interesting applications, clearly. And you need to chase pointers. If you want to find A over here, today, you have a lot of data movement. You go through the memory, and you chase pointers, and you're bound by the latency of memory significantly. Hopefully that's clear. You have serialized and irregular access pattern. Right? And we actually analyze real workloads and real systems. When you're doing pointer chasing, you get 6x higher cycles per instruction compared to other parts of the workload, which is as expected, right? You're really bound by the latency of the memory over here. So our goal was to accelerate pointer chasing inside main memory. The key idea is, again, similar. We have the DRAM layers and the logic layer, and the CPU says find A, and the logic layer does that pointer chasing and returns the data. That would be nice, right? So what are the challenges? Very quickly, CPU core, if it does pointer chasing, it's basically bound by this memory access. In memory accelerator, you can reduce the memory access because you're closer to memory. You're faster for one operation. But the CPU core actually has more parallelism if you're doing multiple pointer chasing at the same time, which is usually the case. In a database, for example, you're serving a lot of requests. If you have a in-memory accelerator that's not parallel, then you're serializing these operations, so you're slower for two operations. So how do you design the in-memory accelerator when you have limited area and budget? Basically, that's the key problem. You can have a simple in-memory accelerator that can be slower than multiple CPU cores, because many CPU cores can be sending requests to this accelerator. But the good thing is the pointer chasing accelerator still spends a long time waiting for memory, because memory is closer, but not that close still. So memory access still 10 to 15 times the latency of computation. So the solution is very simple. It's actually an old idea posed in a different way. The idea is decouple access execute. That's Jim Smith's idea from 1980s. And we use a very similar idea, address access decoupling. You have the CPU cores that are sending pointer chasing requests, and we have an address engine in the accelerator and an access engine. Address engine basically starts accesses, does the computation, and its job is to basically start accesses. And whatever is supplied by the CPU cores, address engine starts those accesses. And access engine sends the memory accesses to memory. And address engine keeps doing computation and sending requests to the access engine. That's the idea. This way you can start many pointer chasing operations or memory accesses in the access engine. And when it's done, you can continue pointer chasing, and you can overlap the latency of address computation and accesses. Yes?
Where's the physical boundary between processor and memory in this?
Oh, in this case, this is what happens in an existing CPU. So this is the accelerator that we have. So there's no.
This is all in memory.
Yeah, this part is all in memory. Yes, this part, exactly. This part is completely in memory. The processor just sends the find request. Yeah. Okay. Okay. So that's the first idea. The address access decoupling enables parallelism in both engines with low cost. That's how you can save. You can get performance. So this is the architecture. Maybe this is going to be more clear right now, but basically this is the DRAM layer, this is the logic layer. Everything over here is in the logic layer. You have the address engine, and you have the access engine. And address engine basically feeds requests to the access engine, and access engine starts those requests and waits for them, and returns the responses to the address engine. And we actually have a cache. So locality is very strong. It's good to have a cache. In fact, in a lot of our works, we need to have a cache in the in-order cores also, because there's still locality You don't want to go to DRAM for every single access. If you can add a small SRAM inside the in-order core, inside your accelerator, that buys you a lot more performance. And this is the communication with the CPU. CPU basically sends a request, and address engine, when it's done with the find request, for example, it sends it back to the CPU. Okay, and this basically shows one traversal going through the access engine, another traversal being pipelined behind it. And, well, and then you keep doing the traversal. Okay, so that's one challenge. So how do you design the accelerator? I think it's really interesting to design these specialized accelerators, and this is specialized for linkless traversal, for example, or any kind of pointer chasing traversal. But there's also an address translation challenge, which is even a bigger challenge in my opinion, because CPU works on virtual addresses, right? You have this pointer that's virtual address. It gets translated inside the CPU. And basically, this is a pretty complicated page table walk in existing systems. Do we want to have the same kind of logic over here? Like, do you actually want to do this page table walk every time you need to have translate the address inside the logic layer if you offloaded this to the logic layer? Not a good idea, right? Okay. So there's no TLB or MMU on the memory side. And duplicating it completely is costly and creates some compatibility issues, because what if you want to couple this with some other CPU that has a different page table structure, right? How do you do that? And I think this is a very hairy problem that somehow needs to be solved. I'm not sure if our solution is the best solution. I don't think so. But there's more to do. Basically, the page table walk requires multiple memory accesses. Our solution is to completely decouple the page table of IMPICA, this accelerator, from the page table of the CPUs. So the idea is this. You have the CPU page table, which basically maps the virtual address space to a physical address space, as you can see that way. And in the IMPICA page table, we're basically going to have a region in the virtual address space that is dedicated to the accelerator. And whatever we're going to operate on, we're going to move it into that region. So everything has to be allocated in that region. And that's the idea over here. Of course, this has limitations, right? How big is that region now? It's a partial to any mapping. And, I mean, you can go into the detail in the paper. It's not really that interesting, I think. In the end, it's very similar to an existing page table structure, but because the address space is smaller, we customize it to the accelerator. So it's not a long walk, and the first region table is actually relatively small over here.
But if you change a page table, the OS knows about this one, so it can sort of shoot down the
Yeah, exactly. So there are those hairy issues that need to be done. No question about that, yes.
Is it possible to move the TLB completely to the accelerator and just send virtual addresses there?
You could do that. I mean, in this case, we're also sending virtual addresses. It's the same thing. So we moved part of.
From the data structure, that is virtual.
Exactly, it's all virtual. Basically, we moved the TLB, but it's not the exact same structure. Basically, we carved out the space in the virtual memory address space, and we're managing only that part. That's the key idea. So if you need even more memory, then you need to do something else, right? But basically, if something changes on the CPU side, yes, certainly you need to shoot down this one. The same mechanism, the same coherence issues exist. And I think this is a very hairy issue, frankly, virtual memory management. If you have processing in memory, how do you do that? There's still a lot more work that needs to be done over here. Okay, flat page table saves one memory access. So there's optimization that's employed over here, which you can read in the paper. I don't think it's really super interesting, frankly. It's something that you need to do. And there's no super big idea over here also. But it works, at least for the workloads that we've examined. So this is, our simulator is also open source. As much as possible, we open source all the simulators that we write. You can take a look at it. And this is what we compare to. So let's look at the Microbenchmark performance. Basically, we looked at 3 Microbenchmark, linked list, hash table, and B-tree. And this is the speed up. And we compare to baseline plus extra 128 kilobyte L2. That's according to our estimations, this is what the cost of IMPICA accelerator is. So 120 kilobyte extra L2 doesn't improve performance that much in these Microbenchmarks because they actually have data sets that are much larger. And linked lists is bound by latency the most, so we get about 90% performance improvement, hash table 30%, B-tree 20%. You can read the paper also. These workloads are also published online. And we imported database, I think this is DB2, I don't remember what it is actually, or DBX1000, sorry. Basically here, with extra 128 kilobyte L2, you gain some performance, 2%. If you give it extra 1 megabyte L2, you get even more performance, 5%. If you do IMPICA, you get about 16% in the database throughput. And we also looked at latency, request response time, basically. Again, you gain some amount of performance improvement if you add more L2, but if you're in memory, you get about minus 13% reduction in the latency. So the results are not that bad, and the cost is not that bad, I think, in terms of what you add. And this is system energy. Again, the microbenchmarks and DBX1000. So of course, linked list gains the most, and database gains little, 6%. And this is entire system energy consumption. It's not just memory. And we calculated the area and power overheads also. You can read the paper. So I think somebody asked the power. Basically, average power actually increases whenever you add some processing. And in this case, we found out it's about 6% of the entire system power. Okay, so we've been also looking at accelerating dependent cache misses without changing the model, basically offloading these dependent cache misses automatically. If you're interested, we can talk about that. This is probably a good place to take a break before we move on to the minimal support. Any questions before we take the break? Yes?
When you talk about increasing power, do you normalize it to account for the increased throughput, or is it just the power?
No, it's just power. This part is power.
So if you increase throughput by 16% and increase power by 5%, you actually improve power efficiency.
Exactly, yeah, exactly. So yes, you can combine the metrics, and I think overall power efficiency improves, no question about that, in all of the workloads we examined. But this power is also interesting for a thermal design point. That's what we wanted to look at.
You're going to cover PIM-enabled instructions there?
Yes, in the minimal support. We're going to talk about some minimal support, such that we don't change the virtual memory system. I think virtual memory system is really hairy. You either do something like Tesseract, which gets rid of the virtual memory system. Everything is physically addressed. It may not be the best option. Or you need to have some translation mechanisms, like this IMPICA, and then you're limited. If someone comes up with a brilliant idea of those translation mechanisms inside the memory, I think that would be great. I'm not really satisfied with what we've done or what anything I've seen, actually, in this area. But I think it's fundamentally not so easy. We need to rethink the virtual memory abstractions for many reasons, for non-volatile memory also. Okay, any questions? Okay, let's take another break. Let's be back at 30, how about 35? That sounds good.